10 minutes late. And we're starting a day late, or 2 days late also, since we had a break on 21st. So we're going to, on the 23rd, which is today, try to cover parts of both of these lectures. The first one here, which I will put in the play mode now, has as its main topic of discussion an interesting device called the trebuchet, which is a catapult involving two angles, and is something that I read about in Scientific American many years ago. It was July '95, if you want to look up this, and it's still the best overall article attempting to describe both the history and the mechanics of this amazing device. But I found it to be, first of all, ingenious. It was called the Ingenium, and the source of the name engineer comes from this device. This was the first engine, which means ingenious something. It probably goes back to some of the stuff around maybe the 10th century. Although the Chinese independently did something very close to this. The medieval ingenium, 9th to 14th century, will talk about that and also show some of the modern reenactments. They have a contest now to throw pumpkins or other stuff into great distances. But the thing I think is most important about this, just as a general knowledge in connection to our culture, is its cultural relevancy. That is, its motion is very human. It's essentially a big throwing person. The human kinesthetics, as they call all of the stuff that makes our body capable of building a culture, connects very well with sports kinesiology, which is the study currently in our university at the athletic department, but is a subject in its own, the physics of human sports. And it turns out, as I'm going to show you, all of the sports that involve levers, like baseball and tennis, are a reenactment of the emotions that build our culture, built our buildings, built everything we are enjoying right now, before the machines made it possible for us to forget that. But we couldn't forget it. We play sports, we become addicted to those sports, particularly golf is a very addictive sport. Now, this will be a chance to really look at a non-trivial application of the generalized curvilinear coordinates that we talked about at Chapter 12 in the review Unit 1. And the stuff that we're doing now is mostly Unit 2, but we covered the GCC mathematics a couple of different ways. A more simple and pedestrian way coming first in this Unit 2, but then Unit 3 goes at it from the full Riemann geometrical tensor analysis. In any case, we'll see the Jacobian relations, the kinetic energy calculation, the dynamic metric tensor, stuff that we saw with polar coordinates in the Chapter 12 of Unit 1. Now, the geometrical topological properties of transformations, we'll skip through that fairly quickly to give you some feeling for how this plays out in the Unit 3. And then, swivel the camera over here to Lecture 18. We're going to quickly go through what we just did in Lecture 17, but we'll come at it from a slightly different angle. And then, this one is where we derive the full Lagrange force equation, following the procedures that we used in Chapter 12, but just a good chance to review. You remember Lemma 1 and Lemma 2, they come up, and we'll just state them without proving them. And then the force analysis. This thing has a pretty good description. What's, I think, really important about the Lagrange or any of these fancy generalized coordinate equations, and that is you get to ignore all those, I should put in here the word pesky, constraint forces for complicated objects. And we need it several times during these series of lectures to concentrate on how that happens. There are a number of different ways to look at that that we'll go through. So I'm going to begin here just showing you a trebuchet. Actually have one sitting on the desk here, and it's aimed at you, but don't worry, this is a very harmless trebuchet that I have on the desk. However, the motion of this thing is quite interesting. So what you really have here is a strangely arranged double pendulum. And later I'll ask you as a homework problem just to work out the complete anharmonic equations of motion for a double pendulum. But this is the one that we'll learn our mechanics and mathematics by going through its various energy, momentum, and all that kind of stuff. Now, I mentioned that this has history, but I'm playing a game here with history in Unit 2. I'm saying, let's suppose that things were kind of like they are now with regard to science, that is the science of mechanics, and let's suppose that Galileo, who had essentially invented mechanics, was asked by the trebuchet generals how to get the best trebuchet. That is, he had to solve the physics problem for a trebuchet. So I'm saying here what Galileo might have tried to solve would be the full motion of this very non-linear system that throws things at incredible velocities for the time.
Dr. Harter, why do you call this a non-linear system?
This is a equation that doesn't just have Hooke's laws. That is, the equations of motion involve powers of the coordinates, as opposed to linear, like the force equation for the harmonic oscillator, which we spent lots of time on. Okay. Now, what Galileo did solve was what the trebuchet does when it's all done throwing, and that is its little arm swings like a pendulum. So that's as far as he got. And there's reasons for that, which I spell out in Unit 2. And you ought to read that because you have to realize that the world didn't need physics for a very long time. And we're not indispensable now. So take that as a little bit of a lesson. But in any case, we can have fun with the trebuchet, and if you have a lot of money, you can build a modern one like this that has the ability to throw a car. And the next slide here shows that car being thrown. It literally takes the car and sends it south at a very high speed. So these are amazing devices that existed for quite a few centuries, and we're going to learn about them a number of different ways. It makes the mechanics, I should think, a lot more interesting. I've learned a great deal just by studying this one problem, and there's more to come, as you'll see. So what we're going to do eventually is treat some of that as well. Here's the early human agricultural and infrastructure building motions that you had to do. A great deal of hammering rocks, breaking the rocks into suitable pieces. Certainly farming, cultivating, and digging. If you had an axe, you would be splitting wood in this country because there were trees everywhere and they were in the way. Throughout the West and the Asian countries, people invented tools that would allow you to cut rice, grain, and various things that we need to eat. I would say this is number one for just numbers of times that this trebuchet motion was done. And you've got to realize that you're going to be doing this essentially every day, practically, if you're a farmer. Let's see, here's splitting wood, here's chopping. Those are very similar motions to trebuchet. Slingshot, that's a biblical thing. Just plain throwing is trebuchet motion. People that in the South raised cattle, Florida particularly, the Spanish ranchers, would crack the bullwhip to push the bulls and the other bovine creatures along. Very different from the cowboys of the western part of the United States. You've probably heard of southern men referred to as crackers. That's where it came from. So there's a trebuchet motion that plays a role, certainly. Now, as I've said, every one of these motions can be mapped more or less isometrically onto sports like baseball and football, because you have to throw, but lever sports are the interesting ones: lacrosse, baseball batting, golf, driving. Of course, this is still the same. People still go out for the fun of it and garden, so there you would be doing that. Tennis is the one that I'm interested in. Both the drive and the serve are helped by knowing some of the physics that we're going to learn from this particular device. So I could add to that the addle-addle, but I'll do that later on. Anyway, this is where it starts. This is where we look at the coordinates that we're going to take, and these are going to be generalized coordinates. We've already talked about a pendulum. A simple enharmonic pendulum could have any angle. That was in our connections to Unit 1 review, Chapter 12. But this one has another pendulum attached to it. That's why I called it double pendulum, but a very strange one that is designed to throw something. Before we go any further, let's just take a look at simulations of the motion and also the real one, which is right here. So I'll start off with this one because this is the one that most likely not to work so well. But what I have here is a major lever and then just a string holding a weight on the attached to the tip of the main lever, and then a heavy steel weight very close to the axis. So I don't have much leverage on this one. This is a trebuchet that's designed not to be dangerous, just to show the motion roughly. Now this trebuchet has an extra degree of freedom, which only showed up around 1200. We'll talk about the siege of Kenilworth later on when we do the Hamiltonian mechanics of the trebuchet. But again, that degree of freedom doesn't play much of a role here. So to cock the trebuchet, you bring this lever down, leaving the mass on the floor there. And there it's cocked, it's ready to go. If I let go of this lever, it should do something, okay, namely throw that washer that's underneath the carriage of the trebuchet. Now, what it could very well do is do a number on me by throwing the washer backwards. And that is something that happens very often when people play with trebuchets. But let's just, I'll just let this thing go and get out of the way. and that's pretty good shot, okay? So you see, even an innocent and purposely designed to be not harmful trebuchet works, pretty well. You can imagine it's just thrown something maybe 100 feet or so, maybe 200, right there. Now, the simulation of this, we have an old program over here that runs on this old computer, and this has been reworked to work on the web, and here is that, and I'll ask the Al to switch back and forth between these. The elegant HTML5 program is over to the right there, and this is as close as we can to that one. We haven't actually tested them one against the other. We can do that now. But let's just look at the motion. Now, what this thing's going to do is it's going to throw the thing I'm choosing here is just animate the simple trebuchet. It's going to throw something. You'll see the mass leave, but then it's going to effectively put the mass back on the end of the trebuchet and go through some motions as though it was left to swing there with the mass having failed to disconnect. So let's just go ahead and run this one. There it goes. And then the mass is back on the end as soon as it leaves, so all I'm doing is letting it follow the equation of motions that we're going to be deriving. And this is, as you can see, what we would call quasi-periodic motion. It follows a set of curves and, in fact, closes on itself, so it may even be, it's very close to being a periodic motion, but it takes it 3 swings to come back on itself. And go ahead and run the same thing on the brand new one, brand new program. And he's got it slowed way down. You have to slow the thing way down in order to, the computer's so fast as it is now. And there it throws it on that screen over there on the right, takes off with a speed of 192. Exactly the same as this one. So, when you do completely different models of the thing, we're getting exactly the same velocity. The final velocity at the leaving point of 93, and these are in English units, miles per hour, with typically gravity, in a range here of 100. Now, the range is a little different. I see the range is
too. We still have a closed path.
Pardon?
It appears we still have a closed path.
And we have the same closed path on both of these. So there's...
Might be the thickness of the bulb. I think that's what it is. It's the radius of the bulb.
It could be. Yeah, that is different, possibly. And everything makes a difference. These things are very sensitive. Now, let's go to the Siege of Kenilworth, which I'll go back here. And this one right here, the Siege of Kenilworth, is the big, fat trebuchet.
In that animation, you have V equals 60, 70, 80. Are those things the velocities of the trebuchet are different XY
on the first throw.
Okay.
The first throw, you see. And the interesting thing is how a lot of the velocity goes in at the beginning. That's one of the things about a trebuchet. Let me just...
But why do you just have XY coordinates?
I'm going to just... Well, let's see if I can
As opposed to
no
non-planar motion.
Yeah.
No, but it's a two-dimensional motion. So what happened to Z?
It's planar motion. Just with y is height.
I guess I don't understand the question.
No, I was just thinking that is it like when you shoot a trebuchet, it's a three-dimensional
I'm going to
motion.
start this one.
So what happened to the Z coordinate? Or like
Planar. The other one's just suppressed. It's in and out of the page.
Okay.
Yeah, we only have 2 degrees of freedom, and they're in line with each other, just as shown in this picture right here. So let me see if I can slow this thing down a little bit here. I'm going to take it way down here, so go slowly. And then start it again with that slowness. Okay, now I'm going to pause right in this region where the force of on the a ball can be nothing but a vector along the red line. The question is, how much energy are you putting in there? And the energy is in F dot V. The velocity is more or less in that direction. The force is in this direction. So we're talking about an F dot V. It's pretty high because the force is large, and there is a good projection on the velocity. That's the thing that you measure power by, F dot V. And so a lot of velocity change going on right here, right at the very beginning. And that's the lesson for the people that play golf and tennis, is that you want to put the energy in as early as possible and have it back.
Which means the motion is highly accelerated at the initial stage.
You direct the energy to the thing that you want to be, which would be the head of whatever lever you're swinging, golf club head or tennis racket face.
Over there, Dr. Harter, what is G 32.2? What is the
Acceleration of Earth's gravity in feet per second.
Oh,
Second.
Yeah.
Oh, okay.
Yeah.
And M1 and M2 are the masses.
Relative masses.
Yeah.
Units, whatever unit you choose.
Yeah. Those are just the driving unit, like our first Super Bowl,
Okay, right.
and this is M2, the second Super Bowl. We're going to make an analogy with that problem as well. This is velocity amplification, but it's highly nonlinear. So that's something we'll discuss later on, but I wanted to point it out. And I also wanted to show you the extreme difference in the behavior for this one. Now, I forget where it is on the HTML.
It's right.
We'll start this one just to show.
Okay.
Again, I'm going to slow this way down because this is really quite spectacular. Let me go ahead and start over again here.
So it's reflected in a different mass again. Base.
Yes, also we've got a monster here. We'll discuss the Siege of Kenilworth. This was reenacted. This is a reenactment that was done on the Science Channel. It was done during the summer over in England. Once again, the English always managed to do the most beautiful work experimentally of the trebuchet. But this behavior that is going on right now, bang, every once in a while you see a thing put a lot of energy into it. This is very chaotic motion. This machine is very nonlinear, and most of its phase space is filled up with what looks like totally random motion. And that's another thing that makes this particular problem interesting. So those are two things that I wanted to point out before we get buried into the geometry and algebra of the Lagrangian and energy, momentum, all that stuff here. Okay, I'm going to let that one run for a while, and you'll see that it really is ergodic. As ergodic as anything can be that only has 2 degrees of freedom.
I can cue that up over here.
And go ahead and do that, because we'll pretty much stick to this screen for the rest of this particular lecture. In any case, the first thing that you do in any mechanics problem, such as what you're going to get on qualifying exams or problems here, is establish the x and y coordinates of every mass point that you have, and later on also establish how those coordinates play a role in determining rotational properties, rotational inertia, and the geometry of that. In this case, we're being very ideal. We're assuming that the actual beam and throwing arm are massless, and that with no friction makes this a pretty special, ideal problem. But nevertheless, it's a difficult problem even with all of those idealizations. So one of the things I caution you to do with a device of some kind that you're doing classical mechanics on is look at its extreme cases. Here is an important point that we'll find is a singularity. That is when the arm is tucked in to the beam. That's a singularity in the Jacobian that you have to worry about. Then there's at right angles. That's an interesting case. And the one I don't have shown is the extreme extension, also singular like the extreme extension. So those are things that have particular coordinates. And also I'm using, just to be annoying, the idea that all rotations are right-handed. So if I go right-handed, I get a positive angle. This is minus whatever you would call a coordinate of rotation. I've turned clockwise here. So with this one, okay? That's a matter of taste. Most people would just say, always show the angles in their positive sense. I like to put the negative in there and see if I can get the sign right for the problem. So here, with a minus theta, I'm going to have a y equal minus r cosine theta. It exhibits the minus signs that you might otherwise leave out. And the big X and the big Y are then given bipolar coordinates. That's the little green rectangle that's making Cartesian out of these angle of theta. So that's the driving weight, big M. And all we need to know about it is a pendulum. But the rest of this problem right here, and there's another way to look at the geometry, sort of simplified somewhat. In this case, this particular angle has been allowed to swing into the positive region as opposed to the negative region. We can write the x and the y components of this into the frame here. So here's one way to do it. This is a little bit more complicated than this particular drawing, in the sense that I've got the thing tucked in here and here. Okay, that's a minus phi there. So this particular x coordinate, which is pointing in the negative direction, is minus L sine of that angle, which is minus theta. So we have here those that's Cartesian coordinate for this mass over here. This is the y coordinate of the thing here. We have let's see if that's correct right there. We got xr coming from here. We're doing everything from the origin here. Okay. So probably a good idea to do that. Let's see if there's anything else. Yeah, this is showing you the fulcrum. For here's the R, and then here's the fulcrum point right here, and here's the script L, which is the length of the throwing arm. Okay, then it has coordinates y and x sub L. That is the thing associated with the throwing arm. So the idea is to obtain the Cartesian coordinates of the each mass. In this case, we're worried about the payload or projectile mass M. Let's see if there's anything else I need to say here. I think that's pretty much it. Let's see. Yeah. So using these as our x and y axis, we're building the Cartesian coordinates for this thing. So the whole idea is that, sure, we'll have generalized coordinates phi and theta, but we've got to write the F equal ma parts of that equation of motion. And here you can see the pieces of this thing, xl equal L sine phi, yl equal L cosine phi, fairly obvious. And I'm adding for the x that little guy to this. So that's one equation. And the y equation, I'm subtracting, getting a difference between those two. Okay? Now, once you have a Cartesian equation, and it's trivial to take partial derivatives and get the first differentials. First the differentials for the big X and big Y of the driving mass, and then the differentials for the payload, the projectile. And what we're seeing for the using the equations that we have X and Y here, big X and big Y here, that we only have something that's dependent on the main angle theta. But this one involves both, obviously, because this is taking a ride on the lever with angle theta. Now, at this point, we mentioned that we're assuming friction-free motion for these bearings. We're assuming that the beams don't stretch or bend. They're not made of a rubber band right here. If we have a rubber band here, then we don't have this constraint right here, that the x squared plus y squared, this is lowercase x and y, should be a constant. Or this one right here for the throwing arm, that's a constraint. And then, of course, there's a constraint for that little piece of the main arm. We're not assuming that doesn't stretch. If they do, then they become generalized coordinates too. The R, the L, maybe even this one right here. And of course, if they stretch, they probably bend, so that adds another degree of freedom for them. So you can see how a mechanics problem can get pretty hairy very quickly because of the number of variables that you have to deal with. We just have two. We have two generalized coordinates to describe all the things that we're going to let this machine vary. Okay, but we have more Cartesian coordinates, big X, big Y, little x, and little y is 4, than we do actual coordinates that we're allowing here. So between the constraints and the geometry that gives the constraints, we're going to lose 2 of the 4 that are in the rows of this, what I would call a raw Jacobian. My terminology for Jacobian that's not square. So what we have to do is we have to look through this Jacobian and find sub-Jacobians that don't give us a 0 value, a 0 which would make it useless. This one fails that I picked right here. The determinant of that thing right there is always 0, always singular.
So, Dr. Harter,
not going to do anything for us.
Does that mean that, like here, when we make a coordinate transformation, we reduce the problem from 4 degrees of freedom to 2 degrees of freedom?
That's right, because effectively we had 2 constraints that were independent. Now later we're going to handle constraints in a funny kind of way, other ways. This is at the end of Unit 3. Lagrange multipliers, all kinds of other funny techniques that you can use to handle constraints. The point I want to make from the beginning of this is that by doing the Lagrangian formulation, or any of the equations like the Hamiltonian or Riemann that we'll get in just these 2 lectures, you will be able to ignore the constraints. You will be able to ignore those. They do no work, so they should be ignored. And the mathematics that we're doing here will do that automatically, provided we pick the right Jacobian out of this thing. So, and that's not the right one. But that one does work. That's the one we want. This one will be non-singular except at places like that. There it would go to 0. When theta and phi are equal to each other, or pi only have a difference of pi. So the sign that you get from the determinant of this Jacobian, this sine function, it is the determinant that tells you where your singularities are. And we'll see where those are when we draw out the coordinate system for this thing. So, at this point, we're at the position where we can produce our covariant and contravariant vectors, our metric tensors, all that kind of stuff, and that's what we're going to do. So, kinetic energy calculation, and we'll put the potential in at the very last. So here's how you proceed with something like that. You start with the kinetic energy, and I'm just talking about the payload here. Later on, we'll bring in the kinetic energy of the driver, but that's just a pendulum that we have already looked at, and only needs to be put in the right place with this one to create the kinetic part of the Lagrangian or Hamiltonian. So what I'm going to do is I'm going to write this in sort of a matrix notation where I have the Cartesian coordinates sitting here as a bra and a ket to make 1/2 mv squared for the projectile. And then I'm going to rewrite x dot, y dot, that's these two guys, as a matrix form. That is, they're linear combinations of the velocities, generalized velocities associated with our generalized coordinates, theta dot and phi dot. Sitting there as a bra, sitting here as a ket, okay, row vector, column vector, and then the Jacobian, which are the components that are sitting right as the coefficients of that. That's sort of lemma 1 that we talked about back in chapter 12, and then the whole thing transposed. So the transpose of this times this will make what we call the dynamic metric, kinetic metric of the kinetic energy for this thing. I haven't multiplied these two matrices together yet, but I have transposed them, this one, so they're just ready to be multiplied. I'm trying to find the most efficient bookkeeping that you can use to get through these problems fairly quickly without making mistakes. You have a good paper trail if you follow either this or the one that's shown at the beginning of the next lecture. So there's our kinetic energy right there in terms of the generalized coordinates, theta and phi, time derivatives. That's the 1/2 mv squared of this problem as far as the little mass payload projectile goes. Okay, so we're going to pull those pieces into a metric that includes this one. This one has just the square of theta, so it has one term sitting here multiplying theta dot and theta dot to make mr squared theta dot squared. That's just one addition to this one to make the whole total trebuchet, ideal trebuchet, kinetic energy. And then we go ahead and finish putting this matrix together. Multiply this matrix by that and then multiply that. There's your kinetic energy right there. Yes?
Oh, so your moment of inertia comes naturally with your choice of coordinate transformation. Is it definitely? Because mr squared is the moment of inertia of the ball.
Right, as we pointed out, the generalized coordinates gives you that. There are a bunch of funny moments of inertia that are hidden in this one. And we're going to look at that a little bit later, and that's something that sort of an option in Unit 1. We make a big fuss about how would you second guess this particular formalism to see that you would have this and this. One way to do that is to check it at those very special points, 90 degrees, 0 degrees, and pi, for example. Now here I want to make a point about this thing. We call this G mu nu or GMN or GIJ using Riemann's notation. But this one has masses attached to it. It's got, first of all of the little red M's here are the payload, hot payload, okay? Then the cool green associated with the driver is attached as well. So there are two kinds of mass in this one. When we were talking about polar coordinates before, there's only one kind of mass. I want to make it clear what's involved in having that. The idea is to boil it all down to the same kind of thing we have with just one particle. So once again, there's that outlier for the big driver. All the rest of it is from the projectile. Okay? And the idea is that this thing right here, the dynamic metric, is that. It's the product of the Jacobian transpose times the Jacobian, the way we've set it up here. And this would be a symbolic way to write that. It's the sum over some kinds of mass. We have two kinds here, payload, and it's got the right color for that, but there's also that other guy, this guy, that's in there. Okay, we're summing over all of the possible particles of this device. And we're just talking about point masses for this particular development. So what we've got here is, and this is sort of in Jackson notation, the partial of the position vector for some mass, summed over that mass and its ilk, and another one right here. So we have two covariant vectors that are sitting here that are going to be the generalized, call them unitary if you want to use the old-fashioned notation. So the kinetic energy can be written first as a Cartesian sum over masses, then we've done a transformation so that it comes out to be a combination of q dots, queer coordinates, remember, the generalized coordinates are now phi and theta. Okay, so we're going to end up with a kinetic energy that looks like that. All the masses are hiding inside this gamma mn, and it plays the same role that the real metric in general relativity plays when you're talking about velocities in 4 dimensions. We don't have to worry about that right now. Okay, special cases. Okay, when is the kinetic energy? Very simple. Okay, we start with this thing and take a special case, phi dot theta dot equal to omega, and then let's suppose that phi and theta are equal. That would be a situation something like this, or equal and opposite. Okay? With theta minus phi equal to 0, we're going to lose, let's see, we're going to pick up this guy right here. Let's see. Now, one of the things that's screwy about this one, of course, is that the Jacobian, the original Jacobian, is 0, that is singular, for this particular one. Now, if they're different by pi over 2, okay, that's another case. And you want to see what your, this is just checking your arithmetic at this point, you see. And now you mentioned that the inertia was a square or something times an angular frequency, angular velocity squared. Here it is. And now this time, this thing boils down to, here's the driver, but for the projectile, it's r squared plus l squared.
That's right. Oh, okay. Yeah.
Which is that radius, right? Okay? Probably, if you've seen that, you probably have a lot more confidence about this one. Okay? This one right here is r minus l. Okay? R minus l squared. Right? So that little guy. Okay? And then there's this one, straight up. Okay? Well, then this boils down to r plus l squared. Okay? After you've gone through 3 checks like that, 3 points, probably haven't made a mistake up here. Okay? So we have 2 singular cases, and then we have the orthogonal one. And let me remind you, these coordinates are not orthogonal. Most of the time, this guy comes in here and intersects that at some angle that's not 90 degrees. Only when you're just at the place where they are at right angles, like this one, then and only then do the two coordinate lines meet at a 90-degree angle. It's one place where it does that, no other place. Generally, it does not do that. Okay, now, here is something that is really Unit 3, where we're worried about the topology of this thing. I want you to notice that the Cartesian coordinates here, x and y, are the same. X equal 1/2 and y equal 2. Okay, puts that mass right there and right there, same place. But this one has a trebuchet this way, and this one has a trebuchet this way. So this is a typical sort of thing where you get this double valued, multi-valued usually, for more complicated systems, that can be very, very vexing. I'll tell you another place where you have it in polar coordinates. Most of the time you look at a plane, nah, I don't see multi-values here. Yes, you do. It's part of a cone. The cone is extended. Which sheet are you on? You see, it's that kind of topology can drive you bonkers with these things, particularly if you're planning to make a quantum trebuchet, where it will occupy both of these. It will occupy this, it's going to go, right? All of the different possibilities for the thing. So this is kind of like spin a half. We'll see how close it is when we go to Unit 4 and actually make the mechanical analog. Now here's something else from Unit 3. There are all kinds of ways to display the coordinates. And one thing I'll ask you to do as a problem is just go and make the thing that looks like a surface. Make the manifold for the various coordinates. That is, hold this at a certain angle, the big theta, the main mass theta, the driver theta, okay? And then let the phi vary, okay? Then you move it to another place, let phi vary again, and so forth, okay? And then, and this is what is not intuitive, but let the phi, and remember, we made a phi that was lab-based. It's not a phi that's measured off of the bar. We'll try that later on. But all of the coordinates, generalized coordinates that I have defined, I forgot to say, I made them so that they're based on inertial frames, not based on this thing that's moving. So, if I take this little guy right here and keep the phi angle the same, okay, relative to the lab, okay, then as it goes, it's always got to maintain that same angle, and it will cut a circle like that, okay? And so those green circles are associated with holding phi constant, the blue, and moving the theta of value to make what looks like a torus. As your eye says, hey, that's kind of round there, isn't it? It looks like a tire, right? But it's not. It's all on the flat, okay? And so then you get into the two surfaces. One of them associated with a trebuchet that's in a left-handed position, and then one that's in the right-handed position. If you draw the two together, it becomes a mess. This really shows that the top of this thing associates with the trebuchets that are in the right-handed position. You see, they're all bent like that. And then the ones on the bottom, I have to break my hand in order to show them, they're left-handed, you see. So there's right-handed trajectories and left-handed trajectories. This equator here is the boundary between right and left. This is a topological consideration as opposed to a geometrical one. But we're using very precise geometry, so you don't need to use that name necessarily. Okay, so this is, I say, what's in jumping between these two chapters, I should say units. 3, which has a topology at the beginning, and Unit 2, which is just to knock out the coordinates and see what you get. But here's where you actually get to see the unitary vectors. Remember, these are covariant, they make tangents. Okay? There's the theta that's tangent to these curves here, which correspond to what you have when you move the theta of the driving mass. This one right here is tangent to these circles that correspond to you moving the payload coordinate without moving the driver coordinate. Now you could just say, the hell with all this stuff, I'm just going to make a Cartesian graph that has theta this way and phi that way. Go ahead. See what it looks like. But see, you know, where you go from right to left. You see, all of these guys are tucked in on this line here. This 45-degree line is the boundary between right and left. And when you wrap this thing up, it goes onto a torus like that. That's a better way to look at it. This is kind of confusing because you don't see really where you are. But it's a perfectly good chart. I think what you call that is a chart in mathematical language that mechanics people use at the advanced levels. So, when we look at a little region like that, then all these blue and green lines make some angle with respect to each other, and it's not orthogonal because these are curvilinear coordinates that aren't orthogonal, they're generalized curvilinear coordinates. All right. Okay, now I'm going to ask you to, draw some of these things with ruler, well, compass. All you need is a compass to draw these things, but you have to know where to put the point. So we'll let you think about this when we do that. Now, here's where we get to calculate what those vectors really are. Here's the Kajobian and the Jacobian that we talked about before. Okay? One of them has the Cartesian coordinates upstairs. That's what I like to call Jacobian. We pointed those out on the wall over there for the three-dimensional one. If you had more dimensions, there would be correspondingly more partial derivatives. We're only two-dimensional right now. X with respect to theta and phi, and y with respect to theta and phi, and those are the derivatives that we have already mentioned. And there are the covariant vectors that correspond to them. They're first column, second column. There's the payload, the driver vector, and there's the payload coordinate phi vector in the second column, right? And once you've got that thing, you can just take its inverse and get this thing right here. That means you have to find the determinant, and then you have to do the inverse thing, which is switch the diagonals for 2 by 2 and then change the sign of the off diagonals. And that's what's going on right here. Okay. Now the color scheme is a little confusing. Here you see the thing that's a function of theta. Used to be in a row, now it's, it used to be in a column, now it's a row. Same thing for the phi here, which is a row here and a column over there. But those rows here, with that extra quotient, correspond to the contravariant vectors. So they will be normal to the various things that their functions are. For example, the E super theta will be normal, that's a gradient, of this particular curve, phi equal a constant. Theta equal a constant. This is theta equal a constant right here for various values of phi. Then this is phi equal a constant for various values of theta. So this little piece of the Trebuchet coordinate system that's infinitesimal, so every curve is a straight line, lets you see where those vectors are at that particular location. You can see it just as easily if you know how to draw a gradient and a tangent, but that is, again, stuff in Unit 3 that we should be aware of even as we go through Unit 2. So the marrying these two is a little bit of a chore, but I think you can do it. We've given enough pictures here to help with that. Okay, so I make the point that the normal space and the tangent space, thing we call covariant and contravariant, are equivalent descriptions of this device. But having those things lets us do algebra more conveniently. And the idea is that any vector that you can think of that would represent something going on with a trebuchet, suppose we put an electric field and the masses have charges, okay, then we'd want to know about the dipoles and things like that. And right here I'm just looking at some vector that's given by components on covariant vectors. They have to be contravariant components. We talked about that in chapter 12, unit 1. And it also can be written in terms of contravariant vectors, but then you have to use covariant components. The idea, you see, is that whatever vector I'm describing here is something that is part of a physics laboratory. It's not something that depends on how you look at it. It's not something that depends on which coordinate system you're using or which variant, co or contra, that you're using. This is an invariant to choice of coordinates, this thing. It's assumed to be a piece of physics that's out, and it's just going to sit there and you can look at it with any sort of coordinates you want. So I'm going to say that all these different descriptions, see, I have a different, completely different set of coordinates that I want to use on this trebuchet, like Cartesian, but I'm just indicating them here by bars. Well, they have covariant and contravariant too. Maybe they're not distinct even, as it would in the case of Cartesian. They'd be the same. I would only have one thing here. But if it's I find out that some other very convenient coordinate system, much more convenient, this one, say one that's relative to the beam for the payload, well, I'm going to give it another name. I'm going to put bar on it, or a prime. Bars are probably easier to write. They don't get lost as easily. So that's what I'll use. All of those are equal to whatever the physics thing is. And same thing for another vector. If I have another vector that I want to go and write in 4 different ways, I'm free to do it. Okay? Now, given any vector here like u, where the u are contravariant components here, okay, they've got their indices up, like the iron and contras holding their knives, and then the co's are more obedient. They have their indices down. And see, the idea is that the covariant component is simply that physics vector dotted with the covariant vector, and the contravariant component has its contravariant vector that you dot that particular u. So I'm trying to review this in such a way that you can see how it's really quite simple once you get used to it. Here's a vector being written in the notation that we're using here. Here's the same vector being written in the notation that the normal space would use as opposed to the tangent space over here. And then there are the actual values of components, various components. And there's quite a mess of them, so to speak. You can either make a parallelogram or you can just do a straight projection and call it a coordinate. I'm going to have you do some exercises to get used to these, because if you do actually look at the length of a vector here and here, we're going to show later that you have to put the metric, square roots of the metric coefficients for them in order to get the right answers. But these various coordinates here, and this one is really extreme. I mean, that's, somebody might want to use a coordinate like that. Well, how long is it? Well, that's how long it is. So getting to know this stuff involves this much detail, but that's kind of it. After you get used to this, you have it. Now the transformation, say, between the unbarred and the barred, coordinates, that's something we talked about, okay? You have a contravariant vector for a frame made of these square coordinates. If somebody comes along and says, oh, don't use those square coordinates, I've got a much better one for you that diagonalizes some matrix or something like that. You got to have some new vectors as well as these new coordinates. Well, how do you get these new vectors from the old? Okay? Well, for example, what I would do here is I'd say, okay, here's my old vector. It's defined as a contravariant. That means it's got the Q upstairs and the Cartesian down the stairs. Then I do what I call a chainsaw sum rule. Take a chainsaw and hack the fraction over there and slide them over. Then I put in the middle here a sum over the coordinates that I want to transform to. Okay? Now you see right here is a partial with respect to r of the new bar coordinates. That's going to be E bar M bar right there. And here's the transformation, the Jacobian. The Jacobian between these two queer coordinates. This is a full-blown generalized curvilinear Jacobian right here. And that's the transformation that you need in order to relate your old guys to the new ones.
Dr. Harter, here we are summing over all the M bar.
And yes, thank you for noting that. Whenever you have two indices repeated on one side only, you sum over all its possibilities, which in this case are 2. Okay? Yeah, thank you for that. Okay? Same deal with the covariance. Chainsaw sum them, and then sum over M bar here. Okay, that's the repeated index on that side. Make sure you have exactly the same character of index here. This is a contravariant index in the denominator, which is equivalent to covariant. That is a covariant. This is a covariant thing, whereas this is a contravariant thing right there. Okay? So that gives you immediately the transformation relation for these weird vectors, quite apart from their components. You may not even have to work with those components, but you should know about them. Okay? Now, this also implies that the actual numerical components that make up this thing use the same transformation. You see, this is nothing but a scalar product. This thing's an invariant. So if I figured out how this transforms, I've also figured out how this transforms. So therefore, I have the same rule. If I've got a contravariant M here, I've got to put that curvilinear coordinate on the upstairs of the fraction of the differentiator. And then this thing is a sum so that I cancel, you see, that particular transformation behavior. The M bar have a contravariant with a contravariant, leaving me with the contravariant associated with the original coordinate system, EM. And the same thing over here for the covariance. Okay? So just by knowing a few simple things, you've got all the transformation rules that you need for each index, either covariant or contravariant, either a vector like an E or a component that is involved in actually getting lengths on a piece of graph paper. Okay, now remember that this stuff is played out in other fields. Dirac notation, equivalence, okay? What did you do here? You had a vector, okay? It was a bra. I like to think of covariance as bras sometimes, okay? And so what do? I take this vector and multiply it by 1. That's equivalent to chainsaw sum, where I put in something that adds up to a delta function, a 1, a unit, okay? And what I'm doing here is summing over M bars, both bra and ket. That's your quantum mechanical completeness relation, right? So I end up there with a sum over those coefficients, those transformations, you see, and that's equivalent to that, of a new vector. That's this guy right here, which is this guy right here. Okay? And that implies that these components of a state will also transform that way. there's the ket transformations over here, which are equivalent, if you wanted to, you make this analogy with the covariance, where the bras are being assigned the name contra. Okay, so these are bookkeeping details that cross fields, quantum and classical technology and with general relativity, very much so. Metric tensors. Now, this is the old-fashioned notation of Riemann for things that are geometric. What we're going to be doing, of course, is replacing these with gammas, because our vectors are going to have masses hiding in them for a mechanics problem. But that shouldn't, if you're careful, make a difference. The mixed covariant contravariant, remember, this guy that has indices up and down, that's this thing. That one is really simple. This one is kind of like what we get when we're talking about the Hamiltonian. This is kind of like the Estrongian, and then this is kind of like the Lagrangian. And remember that this guy right here actually is more like the Lagrangian. It's the one that works off of the velocities. The Hamiltonian works off of the contravariant, so it has to have a covariant metric to go with it. So I'm sorry, contravariant metric to go with that one. The momenta are covariant, the velocities are contras because they're coordinate derivatives. So these are the three metric things, and this one is just a delta function, 0 and 1. So delta sub n mn is gmn, and not this when we're doing GCC. For GCC, this thing is that thing. And that point is not made in any of the books I know, but it should be made. Okay? Now, one other thing. Remember the square roots of metrics that I showed you there? Here's how they come about. If you want to know what the actual length of one of our covariant vectors is, that is the square root of that vector EM dotted with itself, that's GMM. So it's the square root of GM is the actual length of the covariant vector, and G contra MM square root is the length of the contras. So that's an important little relation there. Now there are other relations that we'll come upon as we go through this stuff. One of them is area. Okay, that is, if you have two vectors, one of them a contravariant component with a covariant vector, that's vector, let's say V1, and then there's another one that involves a second component, V2. Okay, the cross product of those is area. That is the area of a parallelogram, space spanned by those. Okay, so you get the product of the components, and then you get E1 cross E2. Okay, now that's the square root of E1 cross E2 dot E1 cross E2, which you can rewrite as a combination here of G11, G22, that's those two, minus G12, and I mean covariant G12 times itself. But they're symmetric, so you can write that 1, 2, 2, 1. In any case, that's equal to that. Dot products commute. So this is the determinant of the metric matrix multiplied by the products of the components that you have attached to those particular vectors. And this works in 3 dimensions as well. What's the volume of a vector that's made out of E sub 1, another one that's made out of E sub 2, and another one that's made just out of E sub 3 with the respective components? Well, those 3 are multiplied together, and then I get the triple cross here, which is the determinant. Okay, determinant of that collection there. Okay, so that's the volume, you see, and what you're seeing is, and you should know this already, is that the volume, this is what you use for general curvilinear coordinate integrals, is the Jacobian's determinant. The metric matrix is J transpose dot J, so it's essentially J squared. But don't forget to transpose it in order to make it work. Now that you know the determinants product, it's a product of the determinants, so you can see the volume can be written very elegantly in terms of either Jacobian, it's a determinant of the Jacobian, or it's a square root of the determinant of the metric. The metric is the Jacobian squared, so you have to take square root of that in order to use it for a volume measurement. These are some more bookkeeping details that are done in lieu of what's now called exterior calculus. And exterior calculus is a calculus of cells of generalized coordinates in which you use only antisymmetric forms. And it's bizarre. It's very powerful, but it's so bizarre we don't have it in curriculum very often. The only book I know of that does a nice job of this, but it does it all spread out through the line, is Wheeler, Meisner, and Thorne. So if you want to learn more about that, that big Bible that's sitting up there is your target. I've tried to teach courses in that, but it's a little bit of a losing deal. Okay, we've got about another 10 minutes, given that we started at 10 minutes, so I'm going to switch over to the other lecture, that is the one that goes with this. And go ahead and stop this very messy collection of chaotic trajectories. You can see as there isn't anything filled that this thing can't reach. I mean, there isn't any empty places except where it can't reach. So that is very much in a different motion than you saw when it just filled up a curve that was looped over itself 3 times.
I have a question.
Yeah.
We took theta dot and phi dot equal to omega, but in this picture sometimes, for example, theta dot is equal to 0, but phi dot is not, or vice versa.
Wait a minute, start over.
We got theta dot equal to phi dot equals to omega in our formulas.
Okay, he says something is equal to omega. I'm not getting the something.
So we took omega dot equal to phi dot equal to theta dot.
Oh, you're talking about different positions of the trebuchet. For example, if I let the beam have a value of theta, say, hanging down, and then I let the throwing arm also be either hanging down or straight up. Okay, that would be pi from the things. That's a singular point. And the singular points, you can see that's where things get very dense in this particular coordinate system. And then in the, and I'll back up here to the one where the torus coordinates were shown. That's the infinitesimal view, but there's more like what you see it from global topology. You see the lines get very dense and close together on the edges here where the little cell that you make, this little parallelograms, collapse. You see, that's where the Jacobian either is infinite or 0. And the Cudjobian is the opposite, 0 or infinite. Those are singular cases. And you can see that's where things get dense there. If I make this thing have the same angle, this blue thing here, have the same angle as the arm, the main arm, then I'm going to reach all the way to the outside, right? If I make that angle pi plus the angle of this, then I'm going to be tucked in on this thing right here, and that means I'm going to be right along that region. So those are regions where the cells, the volumes, either go to 0 or become infinite. Singularities, whole regions of singularities. It's not just one point like polar coordinates, it's a whole line of them. And here too, you see. If the radii are equal, if r is equal to L, that is, the throwing arm is the same as the r, and that in fact is putting it right on the axis there, okay, and then the siege of Kenilworth is very close to that. Then this hole closes up and I have a sort of a super singularity where they're all jammed together right in the center of a torus that's degenerate. You see, so the top line, and then, you know, you could imagine the R getting bigger than L or vice versa. It goes inside. You have the surfaces crossing each other. So there are all sorts of weird geometries that you could have by fooling with just the parameters of this thing. I don't know if that answers what you're asking about, but those are things you want to consider when you first do the problem. You know, to get an idea of, you know, where you're located on a problem that's, I'm assuming that a problem that requires that sort of care would be one where you're doing a real research problem of some kind. I'm not going to expect you here at this university to tackle something like that in a qualifying thing. That would be totally mean. We're not mean. At least we don't try not to be mean. Okay. All right. Let's go over here to. I'm going to have to close this guy out here. Lecture 18, where we review the geometry, and I'm going to just try to get through the derivation, just so you can see what's going on. I think I will also take this one with me, Lecture 18, play it over on this side, so that, and use them to compare when we get some stuff that's really complicated going here. So once again, here's the main picture of what we're talking about, and then here's the geometry of the trebuchet, and I'll set this one up so that we can follow along, comparing consecutive slides that we might need here. There we are, and let me stick to this so I don't drive Al crazy with the camera. Come back to this one, and when needed I will stop this one and go over to the other one. And here is this one right here. Okay, so here are the main coordinates, xr and yr. Okay, that determines where the tip of the main lever is, and then the throwing arm has got to have something added to those two. And meanwhile, the mass is just sitting here at its polar coordinates. Now notice once again, this is important, all of these coordinates are based on star fixed frame. Okay, I'm not measuring this thing off anything that moves. And that's a good start. That for many problems, might be the one that finishes it. We'll see that to do Hamiltonian mechanics, we want to try some other stuff. There are various things called contact transformations that take you to those situations and help you solve them. But here are the, shall we say, polar coordinates of the throwing arm relative to the tip of the beam arm, little r, which is actually a big arm, okay? So I need to go minus r sine theta plus L sine phi. Here, this is the x distance, okay? That's giving me that, okay? And once I've got that, I can take the time derivative of it and then begin to calculate the kinetic energy by simply putting these matrices, the ones that relate x to theta and phi, but I don't need that, I need this one, that's the one that relates the velocity of x to the velocity of the generalized, and put those in first the way it's written, and secondly transposed. Okay, this is good review. Okay? And then stick in this one, okay, and multiply it out. I got to multiply this out first and then stick it in. And I'm done. I've got the kinetic energy. Then I have to play the Jacobian game. Already got the Jacobian that works here. So we really didn't have to make a fuss about that. The Jacobian over here isn't really a Jacobian. It's just one term, okay? And that puts that together. Now I've got, from this thing, okay, my dynamic matrix, my metric, dynamic metric, okay? This would be the metric tensor for the whole thing in Cartesian coordinates. It's 4 by 4, because there are 4 degrees of freedom here, 1, 2, 3, 4, x and y's for those, but it's constrained to only need 2. Okay? So, let's do basic force, work, and acceleration. I'm going to go through this fairly quickly. These are things that you need to really study on your own, going through the various steps. But the force, work, and acceleration, you remember, was the starting point in Chapter 12 of Review Unit 1, where we took the Newton's law, F equal ma, which is valid with a constant m. The metric in xy space, Cartesian space, is supposed to be constant, remember. If that's not true, then you've got to do some more work. That's a very generalized kind of mechanics. But Cartesians definitely don't want to have masses that depend on where you are. Relativity comes later and does that, but it needs the Riemann geometry to do it. Now, we're going to write the work here, f dx plus f dy plus little x d little x and little y d little y, okay? And those are supposed to be equal to acceleration times the various differentials of coordinates. So there's Newton's law, work with the work of function. Same thing we did in Chapter 12, what we did with polar coordinates, so it's a little too simple. Okay, now we go ahead and finish that. This fx dx, okay, we know what the dx's are because we're going to be using the partial derivative of x with respect to theta. The various components of the raw Jacobian are relevant here, okay? Here's partial derivative of x with respect to theta. There it is right there. It's our cosine theta. And then we're going to use them again over here because we've got 2 expressions involving just the first differentials of the Cartesians here and then the generalized here. This is an expression involving the force. This is an expression involving mass times acceleration of each of the 4 coordinates that Cartesian would have if we didn't have the constraints at all. We do have the constraints, so we're going to have to play some games here. Now, the game we play first is assume that those variables that we're talking about are independent. I can set this to anything, and then when I'm done doing that, I can take the feed and put myself anywhere the manifold allows. But I have to obey the constraints. I can't pull the little L thing off of its fulcrum. So, by that I mean I'm going to take the differential d theta, just call it 1, and ignore the d phi. I'm going to do the same thing with the phi, ignoring the theta. So I'm going to have 2 relations here that involve f equal ma, and all of the relevant partial derivatives with respect to the angles in question. Okay? You see, I'm trying to lay this thing out in such a way that you can see how everything gets put together and what it is that works. Right? Now the Lagrange trickery has basically 4 steps. Okay? Each of these equations here involves a acceleration and a partial that comes from our Jacobian. And I'm going to want to rewrite that using this identity for derivative of x dot u, that becomes x dot dot u plus x dot u dot. That's what I'm doing right here. Recall that that was a trick that we did fairly late in the other. I'm doing it right now. And then step D is to use lemma 1 and lemma 2 on these. Okay, I want to turn the partial x dot with respect to q dot and maybe partial x with respect to q, or vice versa. And I want to change this thing right here, partial x dot with respect to q, to a total time derivative of partial x with respect to q. Also, I can get Lagrange's form. That's Lagrange's trickery. Okay? And then finally, I'm going to be able to, if I do that, write it as a time derivative of the partial with respect to theta dot of just the x dot coordinate. That's all we're working with in this example right at the top here. Okay? The same thing there. So I've got 1/4 of the kinetic energy sitting in this parenthesis right here. And it's Lagrange's equation with that. All right? Well, in order to get the whole kinetic energy, I'm going to have to sum these guys all up, all the coordinates up. Okay? So here we sit with d theta equal to 1 and d theta equals 0. These are the situations after we've done the trickery. See? And I've got to sum them. Okay? Once I've summed them, this plus this plus this plus this will be the total kinetic energy, and then I'll have Lagrange's first term, and the second term will follow as a partial derivative of the coordinate theta with respect to kinetic energy if I sum those guys. So this sort of lays it out so you can see what it is that's going on to make these relations. Now, at the same time, I'm going to sum these. Okay? That's got to be the generalized force right there. Now, it's a weird one because it's a generalized force doing a transformation that is four-dimensional. It's quite possible all four of these terms are non-zero. So, adding up first and last columns for each variable, first theta, then phi, you get this guy for the theta, okay? I get that this sum right here, which I'm going to call f theta. So this is a weird, you might say, covariant transformation, but it's got more dimensions than the actual problem. That's the new thing that you didn't have with polar coordinates. So you've got to watch that. Okay, you've got to be aware of that. Same thing with phi. Okay, now we're approaching the limit of our time right here, but you can see what we've done. We've summed up these columns. Okay, and that's giving us what I call the four-wheel drive garbage truck of mechanics. You can take it anywhere because you're already summing everything it has as far as the input. Okay? I'm going to go ahead and get that up on this screen too in preparation to answer any questions about this. But that's about as far as I want to go because that is giving me the Lagrange force equation. Completes the derivation of the covariant force equation, which I call the four-wheel drive garbage truck. Go anywhere and take a load of crap. And if you want to make it into a potential equation, then you better make sure that your force can be written as a potential. These are gravity forces, so yes, you can. So this is, I think we'll just stop with this because this is a heck of a lot of stuff to look at and get used to. It's really something that can go in a very small part of your brain, but right now it looks like it uses the whole thing. So we'll call that a wrap.